Good morning. In this lecture series, we see about the one-dimension problem in shape functions. As last class, we're discussing about how they given the numbering and noding. The numbering and the element is very important for the finite element analysis. While solving the any kind of problem, it's like whether it's a one-dimensional problem or two-dimensional problem. So, next heading is the shaping function. Based upon the topic, the unlocking the mathematical foundation of the computational engineering through the interpolations. So the main function of the shaping function to analyzing the finite element analysis is a more effective and also is a domain discretations. So why is a shape function is a matter in the one-dimensional finite element problems. So as we know that the field interpolations and the continuous solution and domain discretations. So while domain discretations, the finite element analysis, the transformation, the continuous domain into the manageable discrete element and correct with the nodes and enabling the computational solution to the complex engineering problems. And also while analyzing the solving the complex problem, the discretization method is more effective to solve the particular element is more useful for the finite element analysis. And also the field interpolations, the shaping function elegantly interpolating unknown field variable such as like a temperature, displacement, or stress throughout the interior of the element by using only the nodal values. So, based upon your boundary conditions and also based upon your displacement, okay, or force, okay, the particular node number values correspondingly changes. And also the continuous solutions, they also provide the mathematical bridges that enable the calculations of the physical quantities and also the any end arbitrary point within the element and not merely is a discrete noded locations. So dividing the linear shaping functions. So first step, we have to assume the linear variations, and next step is we want to apply the based upon your boundary conditions according to your problem and also solving this simultaneously. So assume the linear variations is we begin the fundamental assumption of the linear behavior within the element. For example, I give us a temperature function with respect to the x means. So the a and b is a arbitrary constants. And the x variable is belongs with the any one of the arbitrary constants. And also the applying the boundary conditions, they enforce known values of the both nodes and establish the two equations. The one is Ti and Tj, the a plus bxi and Ti is nothing but a plus bxj is based upon your x and y coordination system for the two equations. And solving this simultaneously, we have to assume these two equations with the unknown system. We want to calculate the two boundary arbitrary values. So dividing the element shape function, this is the next step for shape function. So here we want to find out the two element main important solution. So one is the coefficient solutions, and another one is the final expressions. So the coefficient solutions is nothing but through the careful algebraic manipulation, we have to obtain the A is equal to Tixj minus Tjxi is by L, and B is equal to Tj minus Ti by L. And the final expressions is nothing but the substituting these coefficient back into the our original equation, that is yield, is this completely interpolation formulas. So it's called as a T of x, the Ti xj minus x by L and Tj x minus xi by L. So here this elegant expressions reveals the how the field variable that's like a T of x is a weighted combination of the nodal value within the weight depends upon your positions. So as per the matrix formation representations, the computation matrix is nothing but T of Ex is nothing but is equal to Six Sjx the whole bracket of Titj. So now this matrix equation we have to assemble, we got to get the Ti and Tj values. So what are the here computational advantages? One, the system is enabled the assembling the global system matrix and also facilitates the automated elements for the formulations and it provides the clear structure for the programming implementations. And the interpolation weightage is nothing but the shape function that serves as the position depends the weighted factor that blended node value the smoothly across the element domain. The closer x is not to a node, the more than the nodal influence the interpolated values. So that summary of the shape functions, as we know that the shape functions, we have to learn the definition and the key properties, and also the element type and the application and impact. While coming the impact, we have to classify as a two. One is the solution accuracy and the convergence rate. The second type is the element type. We have to further classify into three. That is called as a linear element, quadratic element, and a higher order element. So the key property, what are the key property for the shape function in finite element analysis? Utilize its own node, zero at the other node, the inter-element continuity, and the compatibility. Thank you.